Alright, I'm back with another project. Put a few videos up recently regarding amplifier projects, and I haven't really quite finished all of them yet. I'm still working on this little guy right here. It's complete, but got a little noise issue with it, trying to work out. And bought some other little old amps down here I'm still tinkering around with. These little guys. I got two of these little guys here that are old amps from an organ that I'm going to be putting two of them together and making a stereo pair. I'm working on that, but I'm just finishing up something that this little amplifier here. It's a mono amplifier that I purchased on eBay. I don't know why I was fascinated with it. I just saw this little thing and just wanted to get it working to see how it sounds. And it is a kit, or it was a kit, and it was made by Lafayette. And it's an AC/DC amp, which is you don't see these anymore, which means it does not have a power transformer. And just looking at the schematic, and you can see, let me get a pointer, and you can see where the line comes in and goes directly to the rectifier tube, to the filter caps, and then also goes to the various heaters. Each of these tubes uses there's three of them that have 35 volt heaters, and one of them, the 12AX7, is 12 volts AC. So all the heaters are in series. Collectively they make up the 110, 120 volt line voltage. So there's no input, there's no power transformer, and this is the way a lot of these old amps were made. They call them AC/DC because technically you could power them, because there's no isolation transformer, you could power them with a DC source and it would work all the same. So anyway, when I got this amp, it was not working. It had somebody had attempted to build this thing, obviously going through the instruction manual. Someone made little marks, a couple of soldering iron burns. See, everything was checked off. So someone really tried to get it working, but I don't think they ever got it working. And the reason I don't, and this thing was, oh, what year was this? I don't even know if there's a copyright date in here. Looks like 1960. Well, at least this, yeah, 1960. At least this was, the instructions were copyrighted then. So anyway, when I got it, one of the tube sockets was cracked in half, and so I replaced it. This guy right here. I replaced it with a nice new little ceramic guy, and it went through, and this looks like a kind of a mess, but there's really tight quarters down here to working with. But I didn't do my finest. It wasn't my finest hour, but I didn't want to spend a career on this thing. So I went through and replaced all of the capacitors, and I mean all of them, and even the electrolytic, these big 40 microfarad guys that were once housed in this can right there, and that can is not being used anymore. I couldn't find a replacement can capacitor of the right size or of a reasonable cost. But these guys are the same value, and I really struggled to get them in there, but they're in there. And I replaced all of the filament wires with twisted pair that I made myself. And I went through and I traced every single connection, and there were a couple of connections missing and a couple of things not connected correctly, so that's why I don't think it ever worked. And then I fired it up and tested it on the digital storage scope, and I ran some distortion tests on it. And one of the things I like to do is get these little guys working as good as they can possibly be. This, not the greatest design in the world, but at least get it working as good as it can be. And so what I ended up doing, and this is sort of the final stages that I'm documenting this, so I'm not going to show it along the way, but this, I ended up severing the negative feedback. So if you, this little path right here, which comes back to right above the cathode resistor of the input 12AX7, has been cut. And I also end up disabling the bass control, which is right here, and disabling the treble control right here. So the bass and the treble controls do not work. So collectively, by doing that, I ended up getting a much better, a lower percentage of total harmonic distortion, and actually better sound. So this is now a zero negative feedback amplifier. Again, it's a push-pull design. It's now a zero negative feedback amplifier without bass and treble controls. Unfortunately, the input is a little RCA guy right there, so it fits common RCA inputs. And it came with a nice little, this is the original Lafayette box that it came in. So what I'm going to do now, and because this thing is dangerous without anything covering up the bottom, oh, I also replaced the power cord with a polarized cord, and I installed a fuse. And the fuse is in a fuse holder that's wrapped up in this electrical tape right here. So with the polarized power cord, it is actually much safer now than it was, because it came with one of those old style non-polarized cords, which, like this one here, it's in bad shape. So so what I've done is I've made some little wood pieces to go on the edges, and one large wooden piece for the bottom. So I'm going to go ahead and install those, and then hook it up for final testing to see whether our distortion is and frequency response. I don't expect it to be great, but also by severing the negative feedback, I improved, for some reason I improved the harmonic distortion, but increased the noise level. So there is a bit of a 60 hertz hum in the background, which I've tried everything and I can't get rid of it other than reintroducing negative feedback, which helps a little bit, but I didn't want to do that. I think the best compromise is lower distortion with a little bit of noise. With these AC/DC amplifiers without a transformer, every one I've ever heard has a little bit of a 60 hertz hum in the background that was just standard for cheap amps back in the 50s and 60s. So I'm going to go ahead and get these pieces of wood on, and then put the tubes in. Most of these tubes are original. They say Lafayette right on them. And 3 of them do, and they work. And then the 12AX7 input is a mystery tube. I don't know who makes that one, but anyway, go ahead and put this thing together and get it fired up and look at the measurements and check distortion, frequency response, then give it a listen. Alright, so I've assembled the little wooden structure for this thing. Got some little feet on there, drilled some little vent holes in the bottom, just to make it safe, so the wires weren't exposed. And another thing I did is to put this switch, that's the power switch right there. So I installed that power switch because originally this came with the volume knob. It has one of those switches where when you turn it all the way off, it clicks. Click, you turn it on, you adjust the volume. And I always like separate separate switches because with an amp like this, I'm going to probably use it to listen to the radio or some streaming internet station, and I like to set the volume where I like it and turn the amp on and off with the volume having been set to where I like it, so I don't have to keep tinkering with that. But that's the only other modification. So now I've got the thing on. You can see the tubes glowing. These two here are the original Lafayette tubes. I don't know who actually made them, but it's got Lafayette's name on it. And this is a rectifier tube, and this is Lafayette. And this is the 12AX7 mystery tube, but it works. Maybe that was original, I'm not sure. So now I'm going to go ahead and do my final measurements and see what the power output is, what the maximum power output is, and test for distortion, and get some semblance of a frequency response. I don't expect the specifications to be very good. You can see they listed as a 5-watt amplifier. Back in the early 60s, that was always overstated, usually by a significant amount. But for this amp, I'm going to be using it with a high efficiency full range speaker that I built. I'll show you that when I hook it up to for the final listening test. So probably most of the amp's playing time will be in the neighborhood of about 1/8 of a watt. 1 watt with this full range speaker, which is 91 dB sound pressure level. 1 watt, 1 meter, that would be really too loud. So this amp only needs to be about 1/2 a watt, 1/8 of a watt. 1 watt's just, for a little tabletop amp and a little speaker is just too loud. So I'm hoping to get a good watt out of this thing. We'll see. I've done some measurements earlier on when I was tinkering around with the severing the feedback and disabling the bass and treble controls, and that was a while back. I put this amp aside for a while, so I don't even recall what this thing measures at. But let's go ahead and figure that out. So I'm going to be inputting a 1 kilohertz sine wave. Actually, I can't use this. I need to use this is a signal generator, and it doesn't have a very low distortion signal. So I need to use an audio oscillator. Glad I thought of that. I'm trying to get my oscillator out. So I'm going to need to use this audio oscillator, which is low distortion, in order to take distortion measurements. So let me put this down and get this guy hooked up. And then we're going to be using a Heathkit distortion analyzer and a digital storage scope with a spectrum analyzer, just to test things out and get some reasonable estimate of what's going on here. Alright, so I've got my low distortion audio oscillator set to 1 kilohertz sine wave, and have it running into the the RCA jack input. And here's a picture of it on the scope. You can see that it's roughly 1 kilohertz. Right now I've got 1.18 volts RMS. So what I'm interested in doing is I'm going to start out with 1 volt. The pen doesn't work. And let's see, 1 watt is 2.8 volts. We're using a 8 ohm dummy load, so 1 volt will be 1/8 of a watt. 2.8 volts will be 1 watt. And then, so I want to take 1/8 of a watt is typical listening for a high efficiency speaker. For a tabletop amp like this would be typical the power that would be dissipated through a high efficiency speaker with just a normal listening level. So let's take a measurement at 1/8 of a watt, and then we'll go half a watt. And see what the distortion looks like. Okay. So let's start out with 1/8 of a watt, 1 volt. So I'm going to adjust the amplitude to get roughly 1 volt. So 1.006, that's good. And actually, before I do that, let me go ahead and do a spectrum. So, just out of curiosity, we can see that this tall peak here is that's our 1 kilohertz fundamental. Then we have our second and third harmonics. We turn the volume all the way down. Okay, what you're seeing there is just noise. So we start to turn the volume up. You'll see the 1 kilohertz fundamental start rising, and there's going to come a point where we'll start to see the second and third harmonics start peaking up, and that's where things start to get nonlinear. Remember, I disconnected the negative feedback, but that actually improved the performance of the amp. So there you can see, I'm still turning up the volume. There you can see the second and third. Turn it down. So right at that point, things start getting a little nonlinear. So let's go back to measuring. Oops. Turn off the Fourier. Hit the measure button, and we can see that RMS voltage, it's roughly 1 volt. So that's 1 volt is our 1/8 of a watt. So I expect the 1/8 of a watt to be fairly low distortion, and then it'll start rising significantly at 1/2 of a watt. Let's go ahead and let's see. Let's go ahead, and in 1 watt it should go up fairly significantly. Once distortion starts rising, it starts rising. And then I want to find out clipping. Okay, so let me go to 1 watt, which is 2.8 volts, and see what the hold on, I can't turn that up. Okay. That's about as far as I can go. My little audio oscillator won't put out more than... That's clipping right there. Okay, that's 4. Alright, let me get back down. Here we go. I figured it out. Okay, 2.8 volts, that's 1 watt. Now let's look at the spectrum. And you can see that the second harmonic's risen. This is a decibel scale, so this is 20 dBs per square here, per division. So you can see that the second harmonic's risen a little bit, third harmonic's gone up significantly, so I'd expect at 1 watt to see fairly significant distortion. Now let's go back to clipping and find out where that is. Turn off the Fourier. Okay, I'm going to crank the volume up to a point where it clips. So you can do, there it is right there. Nice and symmetrical. So there's our flat tops. So right there it starts clipping. And let's get a voltage reading on that one. Hang on a second. Let me back it down a little bit. And I just want right before clipping, right there. Okay. So voltage is 3.8 volts at clipping. And 3.8 volts power wise is 3.8 squared divided by 8, which is 1.8 watts. So this amplifier is good for 1.8 watts before severe distortion. Take it over the spectrum and look at that right there at the point of clipping. And you can see we've really risen quite a bit on the third harmonic. Look at that, boom, really starts peaking up. Okay, so let me take some real distortion measurements with a distortion measurement device specifically designed to do that, and I'm going to do it at 1/8 of a watt, and then 1 watt, and then somewhere right before clipping. Try that. So hold on a sec. Alright, got the got the Heath kit fired up, and you can see we have 1 volt across our 8 ohm load RMS, and here's our 1 volt on the voltmeter set to the voltmeter right now. So first thing we do before we do distortion is set the level. So I got a level set, and I got to zero this meter out right on the 10 mark. We're going to use percent. We're going to do percentage distortion. Okay, now I've set the level. Now I turn it over to distortion, and I null it out. And I do the fine tuning of the nulling. I'm not going to get any better than that. And we go to auto, and then I start cranking down the meter range and get the distortion reading. So I'm on the, right now I'm on the 1% scale, meaning that 10 mark is 1%. So we're at 0.7%. 0.7% THD, not bad at 1/8 of a watt. Write that down. Okay, let me go back to the voltmeter and crank up the voltage to 2.8 volts. To get our 1 watt across an 8 ohm load, and repeat the process. Okay, we set the level. And go to distortion, null it out. It's about as good as I can do. Actually should be on manual to do that. Try that again. Okay, now we go to auto and we crank down the scale and find out where we are. Okay, it's going to be a lot. Okay, I'm on the 10% scale. So looking at the 10, it's 10%, and it's almost 4%. It's 3.6% THD, which I expected at 1 watt because we saw the spectrum. Go back to the spectrum. Yeah, you see, we saw the second and third harmonics really peaking up there. So 3% at 1 watt. And again, this is a inexpensive amplifier, a kit, so I wouldn't expect this to be any different, actually. And just out of curiosity, we said that 3.8 volts was near clipping, so let's go ahead and try that out. I'll measure. It's hard to do this with one hand while holding the camera. Okay, 3.9. Let me go to 3.8. It's right there, but 3.84, 3.9. Okay, you can see it's really starting to clip. Okay. It says 4 volts on the Heathkit. Heathkit's a true RMS voltmeter. I don't think this digital storage scope is true RMS. So they're going to be off a little bit. But anyway, let's go ahead and set the level. Alright, okay, there we go. Turn this to manual. And now we go to distortion. We start to null it out again. By nulling it out, it's just a very sensitive filter that eradicates or filters out the fundamental frequency of 1 kilohertz. And anything remaining that's not the fundamental frequency are the harmonics. And that's how we know. And we compare the voltages of the harmonics to the level of the fundamental, and then we get our percentage THD. Does it all in an analog way in this old meter. Okay, I'm nulled out. We go to auto, and I'm on the 10% scale, and right now that is a little over 6% THD at 3.8 volts or 1.8 watts. Okay, so now we know that somewhere between 1/8 of a watt and 1 watt, we go from 0.7% to oh, I didn't even write that down, to 3% THD, I think, something like that. I forgot. But anyway, it's working. I just wanted to get an idea of the frequency response at this point also. So let me go ahead and disconnect the distortion. Okay, we're disconnected, and I want to reintroduce the signal generator for this part. So hang on a second, let me get that taken care of. Okay, for frequency response, I'm going to be starting out at, for the upper frequency response, I'm going to be starting out at 6 kilohertz and sweep it through 20 and find out where the the half power point is. So to do that, we're looking at roughly 0.6 volts, and the half power point would be when we go down to 0.4 volts. I'm just going to blur this right here so we can see it rise and fall as I go from 6 kilohertz on up. So now I'm going to be cranking it up 10, 12, 15, 20. Let me go back to 6 and watch what happens. You can see that the voltage level is really starting to fall. We're at 22 kilohertz now, so let me go back to roughly 6 kilohertz. We're doing the upper end right now. I'll do the lower end later. So I'm at roughly 0.6 volts, and I want to find out at what frequency we fall to 0.4 volts. And that'll be our half power point. So now we're falling for 20 millivolts. There we go. There's our 0.4 volts, and we are at 15.8 kilohertz. So the upper end is around 15 kilohertz. It's to be expected with an amp like this. So now let me go down to the lower frequencies. And we'll go a little lower than that. Okay. We start out at 100 hertz. And once again we have 590 millivolts, close enough for this purpose right here. And we start going down in frequency till we get to 400 millivolts. Now I'm down to 60 hertz, 50. Now we're going down. There we go. Let me go back up at 300 millivolts there. When you get to 400, and there we go, 398, close enough, and that's 26 hertz. So our half power point on the lower end is 26 hertz, not bad. Ooh, something happened to the waveform there. That looks weird. Something happened. Because that is not right. Look at that. I wonder if that's my signal generator. It's 14 hertz. We go up to back to 118 hertz. That looks pretty good. We start going down again. Lower the voltage. We start going down in frequency. And we get down to 25 hertz. Something weird happens. Yeah, it's a little odd. I didn't see that before. That sine wave gets really strange at around, that's 15 hertz now, and here's 10 hertz. Look at that, that's weird. So when you go down in low frequency, something odd happens. But anyway, so let me go back to 30 hertz and it starts to look a little more normal. And then boom, it pops into 37 hertz, pops right in. Still looks a little weird at 37 hertz. It's not. There's 67, 70. Look at that on the spectrum. Okay, we're at a fairly low level, so the distortion introduced here should not have anything to do with power. Now it has to do with frequency. So I'm at 70 hertz. I'm going to start going down at 90. Okay, let me go down the other way and see what happens. Now at 30, 6 hertz. Okay, let me go back up to 12. So there's a lot of down at the lower end of the harmonics, a lot of weird stuff starts getting introduced at low frequencies. And now I'm taking up to 59 hertz and 60 and 80 and 100, and it kind of goes away. So it's like, that's really strange. Never saw that before. But that's the way it is, because this amp is as good as it gets per the design. I'm certainly not going to redesign it. So we know that somewhere in low frequencies some distortion is introduced. Okay, well, never saw that before, but that is the way it is. Okay, so we have a decent frequency response. Now I'm going to hook it up to a speaker and listen to it. Let's see if we can hear anything odd going on. So stand by. Alright, just out of curiosity, I hooked up the other trace, which is the yellow trace, to the input, which is the output of the signal generator, and the red trace is the across the speaker, or the dummy load, so it's the output of the amplifier. And you can see, okay, I'm at 23 hertz right now. Let me get some measurements here. 23 hertz. And you can see that the output of the amplifier looks really distorted. And the input looks just fine. You know, let me just bump it all the way up to 216 hertz. And we can see everything looks good there. Looking good. Now we go back down. It's 40 hertz. And you can just start to see something happening around 40 hertz. The waveform is getting strange. I suspect that has to do with the output transformer. Some kind of saturation or some kind of magnetic effects. Look at that. I'm at 16 hertz now. It's really weird. It's really starting to turn into a triangle. You see what the square wave response looks like. Okay. Hang on a second. Yeah, look at that. Let me go to start out around 10 kilohertz. Gracious. So the yellow trace is the input, and you can see that the square wave is really really sloped, and that's just indicative of upper frequency roll off. And you go up in frequency, and then turns it into a triangle, so it's really rolling off the frequencies. Now I'm at 22 kilohertz. And we go down to 500 hertz right now, and it's starting to reproduce something that looks like a square wave, but now you can see the lower frequency distortion. And let me go down to 48 hertz and see what's going on. Oof. That's not good. Oh, even my signal generator is looking a little goofy on that one. It's not a great square wave input. Anyway. So, not the most impressive of specs on this thing for sure. But let me go ahead and give it a listen, see how it sounds. Okay, got it hooked up to some audio, and this is my little speaker. I build these little speakers out of a cigar box, and it's a little full range speaker, vented, and 91 dB SPL. Awesome little speakers. It's a little. I've tried Fostex. I like full range speakers, and I've got some Fostex over here that I use, that I built, and they sound good too. But this is a little 3-inch guy that I use for tabletop stuff, and the driver is made by Fatale, if that's pronounced right. And I've tried a lot of different full range drivers. This little guy, little 3-inch Fatale 8 ohm. They make a 4 ohm version. I think the model number is 25 or something. But anyway, awesome little speaker. Sounds great. So I happen to, what's on my queue tonight? I've got a whole Kraftwerk album on here. Kraftwerk. If I can find the play button here. Let's try something by, there we go. It's a live album. No scratching or noise in the pot. I cleaned out the potentiometers.
Only takes a camera to change your mind.
Sounds pretty good. Because I'm in my workshop, the furnace is running behind me, so you can't hear, but there's a little bit of hum, a little bit of 60 hertz buzzing in there, but not much. I can't hear it from 3 feet away. Find something different to play. Here's an interesting one. Another brick in the wall bluegrass version. Let's see what that sounds like.
Daddy, what else did you leave for me? Daddy, what else did you leave for me? All in all, it's just another brick in the wall. All in all, it's just another brick in the wall.
Sounds pretty good. Really hear any significant distortion. I don't know what that stuff was I saw on the bass. That's really odd. I've never seen that before, but I almost want to measure it again just to see, but nah, it's okay. I'm done with this thing. This is as good as it's going to get. It's a nice little amp. Got the original like Bakelite knobs that came with it, and this is a brass plate. And doesn't look half bad in this little makeshift wood thing that I made.
I don't need no arms around me.
Lafayette model KT92 restored. One of the things I like to do is buy these old amps that they're destined for the trash bin, I guess. Probably this one was. Unfortunately, someone sold it on eBay, and they described it properly as not working, and I didn't care. I just wanted to see if I could get this thing up and running, and this is kind of a neat thing, because whoever built this thing I don't think they ever got it running, because of what I found inside. So after 1960, so 50 years later, more than 50 years later, this amp's been sitting around somewhere and it's finally running. And not half bad either. So now this little guy's got new life, and it sounds pretty good. I'm probably just going to sell them on eBay, listen to it for a while, and pick up another project. Like these old guys down here, like this thing. Got this on eBay. It's an amp from an organ, and still working on a couple more. Trying to give new life to these things. So thanks for watching. You know, I'm gonna do one more thing. It sounds, I don't know, the amp sounds so good. I'm really skeptical about that weird bass measurement. I think I'm gonna measure it one more time, because one of the things I did is I realized when I was testing it, I wasn't testing it with the 12AX7 tube that came with it. It was another one that happened to be laying around, and I put the right one in. I don't know if that was the cause of it. So let me run another real quick test and see if that really does distort in the bass frequencies, because I don't hear it.
Teacher, leave them cares alone.
Well, this thing really has the tube sound in spades. It really has that tube sound, especially in the vocals. Really nice. Take another measurement, I'm just curious. Okay, once again it's showing the same results. So I'm at 30 Hertz now, and you can see when I go down to 20, that sine wave gets really goofy. And somewhere around 45 Hertz it straightens out. 50 Hertz it looks good. So you can see that somewhere in the lower frequencies it really starts to distort. And again, I think that's this is with the original 12AX7, so it's inherent to the design. Maybe I can't imagine removing the negative feedback would cause that, because negative feedback on a tube amplifier is not. It's different from a transistor amplifier. On a tube amplifier, negative feedback is much more conservatively applied. There isn't nearly as much, and it's for purposes of reducing noise more than distortion. You cannot have a high negative feedback tube amplifier, because too much negative feedback will cause instability in the amplifier for various reasons, because of the various phase shifts that happen to the signal throughout the gain stages and then through the output transformer and the various capacitors along the way, that sort of thing. So the open loop distortion characteristics should be pretty consistent, and the negative feedback should just reduce the noise a little bit and have not that much impact on the distortion measurement. So this is something inherent to the design. But again, this is an inexpensive little kit amplifier, so I wouldn't expect this to perform superbly. However, it sounded really good, and it had that, I mean, you want to talk about a tube sound. This thing had the tube sound, which is really nice, really warm sounding, awesome vocals. And I didn't hear anything odd in the bass. It sounded pretty good, actually. So that's the way it is. Well, anyway, Gonna hook this thing up and listen to it for a while. So thanks for watching. Interesting. I'm probably gonna sell this thing on eBay eventually and start a new project, but resurrected this thing from the trash heap. Original tubes, at least 3 out of the 4 are. All new capacitors. Bypassed tone controls. Have a new power switch. Clean the pots. Sounds good. Take care. Night.